This is intro to the collision algorithm, better known or perhaps more fondly known as the baby step giant step algorithm. So the collision algorithm is a type of attack against different types of public key cryptography like elliptic curve cryptography and RSA encryption. It can be used by a third-party attacker to compute information that is supposed to be very time-consuming to compute in public key cryptography a bit more efficiently. It's by no means perfect and still not efficient enough to be utilized in a reasonable amount of time, but it is far more effective than trial and error attacks that I've discussed in my earlier videos. So in the first portion of this video, I'm going to talk about the baby step giant step algorithm in the context of elliptic curve cryptography. And in the second portion of this video, I'm going to talk about the baby step giant step algorithm in the context of RSA encryption. So let's get started. So you'll recall that in elliptic curve cryptography, there's this hypothetical person named Alice who has multiplied a secret value called alpha, by the publicly available generator point G to attain another coordinate point, let's say A, which she publishes. You'll recall that there's an individual named Bob who does pretty much the same thing. He has some secret value that he's picked, beta, and he multiplies that by the generator point G, which is publicly available, to attain another coordinate point called B, which he publishes. And the idea is that Alice and Bob exchange these two coordinate points A and B, and from these 2 points they're able to attain a shared bit of information which they compute using their alpha and beta, Alice her alpha and Bob his beta. And if there's some third party, let's call her Eve, who wants to use either the values of A or B to compute this secret shared information that Bob and Alice can compute, she has a really difficult time doing this because she has neither access to alpha nor beta. And it's these values of alpha and beta that Bob and Alice have that make it possible for them to compute this shared information. But since Eve doesn't have alpha or beta, she cannot compute this shared information. And that's really the foundation of elliptic curve cryptography. If you've got some point A, for example, and you know that A is equivalent to some integer times some other point on the curve, then just given G and A, it's difficult for you to compute alpha. That's the foundation of elliptic curve cryptography. That's what makes it strong. Well, baby step giant step seeks to get around that. Baby step giant step is an algorithm that allows you to compute alpha and beta with a bit more efficiency than if you did by trial and error. It's an attack that a third party like Eve would use. So how does it work? Well, the first thing that Eve would do if she wanted to compute alpha or beta is she would pick an integer m greater than the square root of n, and recall in elliptic curve cryptography that n is the order of the cyclic group, or how many points are in the cyclic group. So let's say that Eve is working with the following public key information. Let's say that she knows that the equation of the elliptic curve is y squared mod 17 is equal to x cubed plus 2x plus 2. She knows that the generator point is 5, 1. She knows that the order of G is 19. She knows that the cofactor is 1. She knows that A is 10, 6. And she knows that B is 7, 6. And let's say that she chooses her integer m to equal 5. 5 is a valid value, since the square root of 19 is approximately 4.36, and 5 is an integer greater than that. So the next thing that Eve is going to do is she's going to compute mg, where g is that generator point of 5, 1. So 5g. Now, if Eve goes through and computes the values of the cyclic group up until 5g, she knows that 5g is 9, 16, if we're working with this public key information. So now the third step that Eve needs to take. So for some number I equals 0 to I equals m minus 1, Eve needs to compute and store I times the generator point g. So in Eve's case, because her m equals 5, she's going to execute the sequence for I equals 0 to I equals 4 and compute and store I times g for the values from 0 to 4. So firstly, we have 0 times g, which is just not defined. So then we have 1 times g, which using the cyclic group, Eve knows this to be 5, 1, because g is just the generator point g that has been released publicly. From there, Eve can compute g plus itself, or 2g, to be 6, 3. And from there, Eve can add 2g to 1g to get 3g, which is 10, 6. And then from here, Eve can compute the last iteration in the sequence, 4g, by adding 3g to g. And in this case, 4g comes out to be 3, 1. So now that Eve has these values, she's going to store them somewhere safe to use for later. Now, the fourth step that Eve is going to take is just a tad bit trickier than the third step. So the fourth step is for j equals 0 to j equals m minus 1, Eve is going to compute and store a or b, depending on whether she's trying to find alpha or beta, minus j times m times the generator point g. So let's say that Eve is trying to calculate alpha. She's going to use a. So the first thing that she's going to do, she has the publicly released information of a. She knows that that's equivalent to 10, 6. And then she's going to subtract j, let's say, this is our first iteration, so this is going to be 0, times her m, which she picked to be 5, times the generator point g. So this is just going to be 10, 6 minus 0g, so this is just going to be 10, 6. Now on the second iteration of this sequence, Eve is going to have 10, 6 minus 1 times 5g, or 10, 6 minus 5g. So then Eve is going to need to compute 5g by using point addition. So she's going to compute 5g to be 9, 16. So she's going to simplify 10, 6 minus 9, 16. And point subtraction in elliptic curve cryptography is fairly similar to point addition in elliptic curve cryptography. So the only difference is that the y-coordinate of one's first point is going to be negative instead of positive. And that's really all the difference for point subtraction on elliptic curves versus point addition. Otherwise, the process is pretty much identical. So after computing 10, 6 minus 9, 16, Eve finds that this is equivalent to 6, 14. And now she'll just keep on going with her sequence. So she'll do 10, 6 minus 2 times 5g, 10, 6 times minus 3 times 5g, 10, 6 minus 4 times 5g, until she's arrived to the point where that iterator j is equal to m minus 1, or j is equal to 4. And she's going to store the values that she gets into a similar list that she did in step 3. So after going through all that hassle, Eve finally has 2 lists that she can work with a bunch of different values in them. So what is she going to do with these 2 lists? Well, she's going to go through them and analyze them, and she's going to figure out the common coordinates between these 2 lists. Now, this is pretty easy for me to do just by looking at it because these are two fairly short lists. I can see that in list 1 we have 10,6, and in list 2 we have 10,6. So these are the two shared values between these two lists. So, I mean, in elliptic curve cryptography schemes where the lists are much, much bigger, you're going to have a program to write this for you and to be able to compare these two lists. But since these two lists are fairly short, it's fairly easy to do this just by looking at it. So after we've realized that our common coordinates are 10,6, what do we do from there? Well, we have to look at the values of I and j that created these two coordinates. So in list 1, what did we do to get 10,6? Well, we multiplied 3 times g together to get 10,6. So our I in this case was 3. I equals 3. And then what did we do to get 10,6 in list 2? Well, we said 10,6, our value of alpha, minus 0 times 5g. So in this case, our j was 0. So j equals 0 in this instance. So now what do? Well, it turns out that the value that Eve is looking for, alpha, mod n, where n once again is the order of g, which in this case happens to be 19, is equal to I plus j times m. Here, we'll just make this the generic n for order of g for right now. So now we'll plug in our values that we've just computed. So alpha mod the order of g, which is 19, is equal to I, which we said was 3 to get that common coordinate, plus j, which we said was 0, times that initial value of m that Eve computed, which was 5. So now we just get alpha mod 19 equals 3. And the only value that alpha is going to take on that can satisfy this requirement is 3. 3 mod 19 equals 3. Well, it's the only value less than 19 that can satisfy this requirement. So we found out, or Eve has found out, that alpha equals 3. And this is the correct value of alpha. If you remember in my earlier video on elliptic curve cryptography, I said that the value that Alice chose to be her alpha was 3. So this is in fact a correct value for the value of alpha, for Alice's value of alpha. So the collision algorithm works for elliptic curve cryptography. We've managed to find alpha in a semi-efficient manner. So that's baby step, giant step for elliptic curve cryptography. How about baby step, giant step for RSA encryption? Well, it's a pretty similar process. If you've seen my earlier videos about decryption techniques in RSA encryption, you know that the expression for decryption in RSA is the ciphertext message raised to some secret integer exponent d for decryption key, mod n, and that should give you the original message m. So in this case, what Eve wants to calculate is not alpha, but d. Now, she can do this using the logarithmic technique that I described in one of my earlier videos about RSA encryption when I talked about the different decryption techniques in RSA. But she can also use the baby step, giant step algorithm, and that's quite more efficient than the logarithmic technique that I was describing in my earlier video. So let's first say that Eve is working with some value of C ciphertext for 53 raised to some decryption key D mod 143. And let's say that she knows that that equals 14. How does she compute D using BSGS? Well, the first thing that she's going to need to do is choose some value k such that k is less than n. So let's say that Eve picks k to be 5. 5 is less than 143. So the next thing that Eve is going to need to do is evaluate and store c mod n, c squared mod n, c cubed mod n until she gets to a value of k such that k is the value that she picked. So the last value here, for example, would be c to the k minus 1 mod n. So that would be c to the 5 minus 1 power mod n, or c to the 4th mod n. So since this is a pretty short list, I can just do this manually. C mod n is equal to 53 mod 143, which is just equal to 53. Next value is c squared mod n, which is equal to 53 squared mod 143, or 92. Next value is c cubed mod n, or 53 cubed mod 143, or 14. And then this final value, this c to the k minus 1, or c to the 5 minus 1, c to the 4th mod n, is equal to 53 to the 4th mod 143, or 27. So now Eve is going to take these values and she's going to store them until she needs them again. Sounding familiar? So now the third step for Eve is a bit more complicated. She's going to evaluate and store x. Now x is going to need to satisfy the requirement. First, for the first value of x, it's going to be c to the 1 times k power x mod n is equal to m. And Eve is going to need to find a value of x that satisfies this requirement. So then the next value of x is going to need to satisfy the requirement c times 2 to the k times 2 to the 2 times k power x mod n is equal to m. She's going to need to find another x that satisfies that requirement. And then Eve is just going to keep on increasing that power right here. 1, 2, 3, 4, so on and so forth, until she gets to some value r, where c times r, c to the r times k power x mod n is equal to m, where r times k is greater than n. And remember, she's not going to store the simplification of this, or she's not going to store m or anything like that. Remember, Eve is storing the value of x that satisfies these requirements. So in this case, how do we know when we get to r? Well, r times Eve's chosen value of k, which we said was 5, has to be greater than n, which we said was 143. So for this to be true, r is going to need to equal 29, because 29 times 5 is 143, and that's the first value 145. And that's the first value that's going to be greater than 143. So we've got quite a bit more iterations to go in this sequence than we did in step 2. But I'll just do the first few to give you the idea. So we're working with this value first. C to the 1 times k power times x mod n is equal to m, and we're looking for a value of x that satisfies that requirement. So we've got c, which is 53, to the 1 times k power, k we said was 5, times x mod n, which we said was 143, is going to need to equal 53. Sorry, 14, not 53. So it turns out that the value of x that satisfies this requirement is 14. We can check that if we want to. 53 to the fifth power is 418,195,493, and that value times 14 is equal to 5,854,736,902, and that value, mod 143, is indeed equal to 14, so we know that the value that we computed for x, 14, is a valid value that satisfies this requirement. So we go ahead and we store this value of 14 in our list. And we're just going to keep on doing that same sequence until we get to c to the r times k power, where again r times k is going to be greater than n, or r is equal to 29. And after we've got all those values, we're just going to go ahead and store them in a list. So now we've got this list 1 and this list 2 with a bunch of values in them. So what do we do from here? Well, you guessed it, we're going to find a common value between these two lists, just like we did with elliptic curve cryptography. So I see right now one value that pops out at me is 14. We've got the value 14 in list 1, and the very first value in list 2 is also 14. Now again, we're going to look at what did we do to get this value of 14 in list 1, and what did we do to get this value of 14 in list 2? Well, in list 1, we did c cubed mod n, which was 53 to the third power, mod 143 to get 14. So what we want here is this exponent 3. So we're just going to keep this off to the side right here, and we're going to say 3 is that exponent that we used to get 14. In list 2, what did we do to get 14? Well, we were working with this very first value right here. We said 53 to the 1 times 5 power times x mod 143 is equal to 14, and we came out with x is equal to 14. And what we're interested in is that value of 1 here, that number that we kept on increasing and increasing and increasing until we got to r. So, but what we're interested in right here is that the value that gave us 14 was 1. So we're just going to put 1 off to the side here. So now what we're going to do is take this value of 1 right here, 1, multiply it by that initial value of k that we chose, or that Eve chose, which is 5. We're going to add 3 to it to come out with 8. And, I mean, you can assign variables for this, but that's the gist of it, is that we multiply this value by the value of k, and then we add the value that we computed right here to that product to come out with 8 in this specific instance. So what is 8? Well, 8 is what we have been looking for. 8 is D. But let's try it out just to be sure. 53 raised to the 8th power is 62,259,690,411,361. And then that whole monstrosity, mod 143, is equal to 14. So BSGS for RSA also works. So BSGS is really an algorithm that's a lot more efficient than a lot of the trial and error techniques that I've been talking about in my earlier videos. It's a meet-in-the-middle algorithm that requires a lot less iterations than a lot of the other techniques I've been discussing. Well, I hope this was helpful, and thank you for listening.